Morning. I hope you guys can stay for 1.5 hours. Wait. Stop the transcription. Okay, so I'll start now. Before we start the lecture for today, okay, so please download the new notes, chapter 6 on week 6. Okay, one is the notes, and then another is look at the book and resources on your dashboard. Okay, on your subject COA, and then go to the books and resources. So there's a file here named MIPS screen sheet. Okay, so download that. It's because of we will start to use the assembly language. Okay, so there is like a code sheet, okay, that you can refer to. So that's the one, and then the new notes also. So I'll just continue with the chapter here. And then once you have downloaded it, you can just open. You will see. So this is the MIPS reference sheet. So whatever instruction that I have been explaining, so it's referring to this reference data. Okay. So on the first page, right? Okay. Right. Bismillahirrahmanirrahim. Salatu wassalam ala asyrafil anbiya wal mursalin wa ala alihi washabbihi ajmain. Bismillahirrahmanirrahim. Right. So for this week, I will introduce you about instruction language of the computer, whereby we will learn about MIPS. So what's inside this chapter is that I would introduce you to assembly language, and the assembly language that we will learn is what we call as MIPS. So I will introduce you about MIPS assembly language, and then I will introduce you also the basic instruction in MIPS assembly language, and then we will go to we will brief about the assembly operands, especially memory. So whereby the instruction that needs to transfer data will be introduced after that. Okay, so LWSW here is instruction for data transfer. And then we also would brief about MIPS decision instruction, BEQ, BNE, and also J instruction, right? So what is the basic job of a CPU? So the basic function, okay, so basic function of a CPU is to execute lots of instruction. Okay, so the keyword is execute. Okay, so CPU would execute. Okay, so but it depends. Okay, what type of data that they need to execute the instruction. So there are many types of instruction, but we will learn about the basic instructions that can be executed by the CPU. So instructions are the primitive operations that the CPU may execute. So different CPU will have a different sets of instruction. So these sets of instruction is depends on the CPU implementations. Okay, so depends on the CPU implementations, which we will call as instruction set architecture. So it depends the architecture family that the CPU was implemented. So for example, we use architecture Intel 8086 for Pentium 4 or the predecessor, okay, so the previous family. So here we can say that this is like a processor for 32 bits, So they have a different instruction set architecture. And then IBM, Motorola, PowerPC have a different architecture. So when you have a different processor architectures and the components inside of it, so they would introduce or implement a different ISA. And then we have a MIPS, and then Intel instruction architecture 64 bits. Okay, so most of the Intel processor employ the 64 bits architecture. Okay, but for the sake of simplicity, okay, so we would learn about 32 bits architecture, right? So in the early trends, okay, they propose to add more and more instruction to the new CPUs to do elaborate operations. Okay, so in fact, one of the architecture called VEX had an instruction to multiply polynomials. So we know that polynomials is a very complicated instruction. Okay, but then Koch, IBM, Patterson, Hennessy, okay, has introduced the RISC philosophy. So you might wondering where comes the IBM here, right? So one of the engineer called COCKE here, Koch, and together with the other Patterson and Hennessy, they propose RISC philosophy or RISC concept, reduced instruction set computing. So the instruction set, okay, was designed to keep the instruction set small and simple, so to make it easier to build fast hardware. So and then they will let the software do complicated operations, okay, by composing a simpler one. Okay, so so in this case, okay, a set, okay, so a set of, okay, 1,000 add operation, okay, so is faster and can be is easier to build compared to a sine, okay, sine wave calculation, okay, because of the complexity of the operation. Okay, so they design it, okay, so to execute a simple instruction, and then, okay, the software engineer would design the complicated instruction, okay, to be executed by this simple processor. So why is that something that the task that very easy for you to do can be executed in a short time? Okay, so when you repeat it, okay, when you repeat the same operation, okay, the same instruction, it would be easier for you because you are more experienced about that, right? And then one day you need to do another complex instruction, which is you don't know how to execute it, so it would take time. So rather than that, they propose that using the same and simple instruction is much better. Okay, so so we will look into the MIPS architecture. Okay, so why is that? It's because of MIPS is much more simple. Okay, so MIPS comes from the semiconductor company that built one of the first commercial RISC architectures. So previously, when Koch, Patterson, and Hennessy proposed this RISC philosophy, see, they also comes out with the MIPS architecture actually. So we will study the MIPS architecture in some details in this class. Okay, so basically you will learn about the basic instructions of assembly language in MIPS. So why MIPS? Okay, instead of Intel 8086. Okay, so because MIPS is simple and elegant. Okay, we don't want to get bogged down in gritty details. Okay, when they propose the MIPS here, they use the same formats. Okay, they use the same format, the same very similar fields. Okay, so very similar operations. Okay, so that it will be easy to remember. Okay, and easy to operate. So MIPS widely used in embedded apps. x86 little used in embedded. Okay, so because Intel 8086, okay, is widely used in the computers, but MIPS is widely used in embedded apps. Okay, as you can see on the figure on my right side. So these are the application or devices or systems that use MIPS. Okay, and more embedded computers than PCs. So if you can see, even the PS2, PSP, and then LaserJet, okay, LaserJet printers, they are driven by MIPS-based 64-bit processors. Okay, what's inside the MIPS? So before we want to learn about the assembly language, okay, I would compare it with the C++. Okay, we compare it with C++. Right. So when you learn about C++, first is that you learn about variables, right? So in assembly, we have variables. Okay, you will learn about variables. So, but for assembly, okay, we refer the variables as registers. Okay, unlike high-level language like C or Java, assembly cannot use variables. Okay, so why not? Remember when the rules about when we try to create a variables, right? There are a wide range of variables that we can create because it can start from characters. Okay, so very case sensitive. We can capital A and small capital A. So we have a lot of varieties. Okay, but for assembly, they cannot use that because it's limited. They want to keep it simple. Okay, to make it fast, so they have to keep it simple. So the assembly cannot use the variables. Okay, assembly operands, okay, are registers. Okay, so all the data, okay, that we store in the variable. So but in this assembly, we store the data in registers. Okay, in the registers. So all operands, okay, are what we call as registers. There are limited number of special locations built directly into the hardware. The hardware here is referring to the CPU. So imagine that small rectangle device, okay, can contain a very limited number of registers. Okay, so to do the operations. Okay, all operations can only be performed on these registers. So what's the benefit of using the registers? Registers are directly implanted, okay, like they soldered on the CPU itself. So they are very fast because since they are very near to the CPU unit, okay, so it's the fastest memory in I can say in the world. Okay, so it means that on the whole system of the computers. Okay, so it's faster than 1 billion of a second. Okay, but the drawback is that since the registers are in hardware, it's a hardware itself. Okay, so it was implanted in the CPU. Okay, so there are a predetermined number of them. So it cannot be called as the variables. Okay, but it can act as the variables. All right. So if it's a hardware, so we have a limited number of them. Okay, so we have to determine how many devices or how many registers that we can put inside the CPU. Okay, so the solution is that when it has a limited number of registers, MIPS code must be very carefully put together to efficiently use the registers. So we have a limited number of registers to do the operations. So when we write the codes, Okay, the MIPS code must be designed, or we must write the code very carefully, okay, to efficiently use these registers. So actually, how many registers that we have in MIPS? Only 32. Okay, so only 32 registers can be used in this MIPS assembly language. So why 32? Okay, why 32? It's because of the smaller the number, the faster the execution can be operated. Okay, so they use 32 registers in MIPS. Another reason is that is because, okay, it's in a base 2 number. So 2 power of 5 is equal to 32. Okay, but previously, okay, previous assembly language that they have learned, they use um, x86 is 32, I think. Okay, but previous version they have used 16, maybe 8. Okay, but when they increase the technology, okay, so thus they increase the numbers of registers in the MIPS. So at the moment, the simplest one is the 32 bits registers. Okay, so it's because of it's a power, it's a base 2, right? So let's say if you want to design, I want to design 31 registers. Is it applicable? Okay, is it applicable? But if you look at the computer itself, they can only understand 0 and 1, right? So only to these two numbers. That's the reason we use the base 2 numbers, okay, in the computer instruction. So let's say if you use a 31 registers, okay, so it's less than 32. Okay, so what about that one registers that is not used? Okay, so what about the one registers that we did not use? Okay, and then let's say if I want to use 60 60 registers. Okay, so if you want to use about 60 registers, so 2 power of 6 is 64. So what about the 4 register that is in the 2 power of 6? So it's a waste. Okay, so rather than that, we use fully. Okay, so the numbers of the registers itself. Okay, so each MIPS register, okay, so what is it? Okay, for one register, okay, so we have 32 registers, right? So one register, okay, the size of that one register is 32 bits wide. Okay, 32 bits wide. It means within that register, it can contain 0, 0, 0, 0, 0, 0, 0. Okay, you times 8 times more, okay, 6 times more to get, okay, 32 bits. Right? So you will get a 32 bits of data. So that's 32 bits wide. Okay, so each of these one register can store 32 bits data. So this group of 32 bits, we would call it as a word. So if the data is in 32 bits, it's also equivalent to one word. We call it as one word, okay? This word, okay, this keyword of one word here would be used on the instruction later on. Okay. Now, the registers, okay, we have 32 registers, right? So they are numbered. Okay, so in order for the CPU to operate the instruction, okay, so we need the registers and then they have to be numbered. So they will be numbered from 0 to 31. So remember, we have 32 registers, which is 2 power of 5. So this 5 here is related to the 5 bits, okay, of the number of registers. So we start at 0 until 1, 1, 1, 1, 1. So here 1, 1, 1, 1, 1 with B is a complemented of 31 decimal. So each register can be referred to by number or name. So where is the here. Okay, so we have a number of registers. When you look at the MIPS screen sheet, okay, look at the first page on the right bottom. Okay, there is a register name, number, use, and call convention, right? When you look at the number there, okay, it starts from number 0 until 31. So this is the registers that they are referring to. Okay, and then so we can refer, okay, using number or name. So here you can also refer using the name. So provided that we use the dollar sign, say $0, $@ $V0, $V1. This is the name of that register, but they are referring to the function of that register. So they have special purpose, right? So we reference the registers by numbers, okay, by using the dollar sign. Okay, so you can also refer the registers using numbers. Okay, so if you want to register, if you want to refer using a register numbers, we use $0, $1, $2, $30 until $31. And then if you want to refer using a name, so you can also refer using a $0, $S1. Okay, so dollar here means the registers. Okay, the registers ID. Right. By convention, each register also has a name to make it easier to code. Okay, so for register 16 until 23, okay, they are named from register S0 until register S7. Okay, so means that you would relate, okay, from register 16, so the name is register S0. So 17 is S1, and then 18 is S2, and then until register 23, okay, is $S7. Okay. And then for register 8 until register 15, okay, the name of that register is $T0 until $T7. $87. Later, I will explain other 16 registers name. Okay, so in general, use names to make your code more readable compared to the number here. Okay, so using the names is much more readable for you to write the code. Okay, so in C, Java variables versus the registers. So in C, and most of the high-level language, so variables are declared first. Okay, you after the int, main, okay, bracket and open curly bracket. So here is the declaration, right? You would declare your variables, right? Here you would declare your variables. For example, variable Fahrenheit is data type integer, Celsius is data type integer also, and then variable A, B, C, D, E is declared as char. Each variable can only represent a value of the type it was declared as and cannot be mixed and matched. So in this case, variable Fahrenheit and Celsius is only a data type of integer whereby it cannot be used to um, represent char in this case. And then if you use it, okay, the compiler will give you an error, right? Okay, so one variable, one data type. But in assembly language, the registers have no type. Okay, so no type, no declaration of integer. Oh, okay. T0 is used for integer. T1 is used for char. No. Okay, they don't have any type. Okay, so they can accept any type of data. Okay, any type of data. So the operations determines how register contents are treated. So if you want to treat the data in the register as integer, then we can use add, subtract, and everything else. But if we want to treat the registers as a char, so we can use a similar type of like a printf or scanf or cout or cin. All right. So there are very similar instruction for that. Okay, and then another um another features in the programming language is that we use comments, right? So another way to make your code more readable is by using comments. Okay, so I bet that you are not familiar with the comment when you are trying to write C in your C++ coding. Okay, so practice more on using the comment so that any programmer who reads that code can refer to the comments. Okay, so in MIPS, okay, we use hashtag. We use hashtag to indicate that that line is a comment. So anything from hash mark to end of line is a comment and will be ignored. Okay, so this is just like the C, not 99, okay? So it should be plus, plus. Okay, so in C++, we use a double slash. Okay, so to indicate the line comment, we call this as a hashtag is a line comment. Okay, so note that different from C, okay, C comments have a format of slash asterisk and then a comment of slash close with a slash asterisk, whereby this type of symbol, okay, can span the comment into many lines. Okay, so the comment can exceed to many lines. Okay, meaning that if you enter and then until you close it with the asterisk and slash, then it will be treated as a comment. Okay, but for assembly, they don't have that features. Okay, so each line must be placed with a hashtag. Okay, so to indicate to the assembler that this is a comment. Okay, this is a comment. Right. So in assembly language, each statement is called instruction. Okay, so you need to remember for a statement in assembly language, okay, usually one statement, one line. Okay, usually one statement, one line. We call that as instruction. So one line or one statement, one instruction. So they would execute exactly one of a short list of a simple command. Unlike in C and most other high-level language, each line of assembly code contains at most one instruction. Okay, as I said, one line of instruction in assembly, okay, contain at most one instruction. Okay, and then instructions are related to operations such that equal here is to initialize. This one is to initialize. Plus, okay, plus is here is add, subtract, multiplication, and division in C or Java. Okay, so for this course, we only learn about the simple one. Okay, you only learn about the simple one. And I can start give you a project requirement using the MIPS. Right, okay, so enough already. I will give you MIPS. Okay, so first is that I would introduce the basic instructions of MIPS, which is addition and subtraction. All right, so this is a very simple instruction. So they have a syntax for this operation. Okay, so remember the syntax, one space. This is a space, eh? This is a space. Okay, and then 1 space 2 comma. Okay, so this is syntax, right? So they use comma here, and then 3 comma 4. So whereby 1 here you would write the name of the operation. 2 here you would write the operand or the variable that would become the destination. Okay, the variable or operand or register's name that would become the destination. And then 3, okay, would become the first operand or first variable that become the source. Okay, first source. Okay, first source for that operation add or subtraction. And then 4 here is the second operand for operation source 2. So if you look here, you can see that the syntax is rigid. Right? It's rigid. They use it in a uniform method. So as you can see, for the operation, we have 1 operator and then 3 operands. Here means variables, and then here means operation. Op means operation. So 1 op and 3 variable. So why? To keep hardware simple via regularity. So in this case, when you learn to convert the instruction to binary numbers, you have one simple way or one uniform way to convert it. Okay, so remember, computer only understand binary, right? So this instruction will be convert into binary. So to keep it simple via regularity, so they keep it the syntax as rigid as possible, right? For example, addition in assembly. Um, Example for MIPS, okay, we use a command add. Okay, add means to add the variable or register S1 and S2 and store it to S0. Okay, so in this case, I would write, maybe I'll open a notepad. Okay, hold on. Okay, continue. System preference. Turn on iCloud. Alright. Alright, so usually I would write my code here. So let's say you want to write ADD and then register S0, comma, register S1, comma, register S2. And then I would tap and then I put my hashtag here. I would write, okay, S0 is equal to A, and then S1 equal to B, and then S2 equal to C, and then A is equal to B plus C, like that. So to tell the other programmers or other who reads my code is that here is A, and then this is B, and then this is C, S2 is C, and then the operation add here means that A is equal to B plus C. So in order for you to understand that. Okay, so that is how I would write my codes in MIPS. And then the equivalent in C was written as the comment. So in order for me to understand what I'm writing at that moment. And then where the MIPS registers is S0, S1, and S2 are associated with the C variables of A, B, and C. So here we can say A, B, and C. So because we have add here, so we can understand that S1 add with S2, and then we will store into S0. Okay, so do the operation on the right side and store the result to the left side like C++. Okay, like C++. Okay, the same can be applied on the subtraction in assembly. We have sub S3, S4, S5. Okay, which is equivalent to D is equal to E minus F. whereby the MIPS register for S3, S4, and S5 are associated with the DEF. So in order for you to remember or to understand which one referred to which one, is that you need to remember, okay, the third column and the fourth column is for the source. So source here means that the one that we need to operate. So E minus F, right? So E and F is the source. And then the result will be stored in D. So E here is referring to S4, F here is referring to S5, and then D here is referring to S3. Okay, it's not because of the position, but it's because of the operation that we need to do. Okay, and then what's the operation? It's the sub. Okay, it's the sub. So you cannot say E here is for S5, F here is for S4. It's because of first source will subtract the value inside second source. Okay, so the position here tells you how they are operated. Okay, and then, so how do the following C statements? Okay, so let's say you have A is equal to B plus C plus D minus E, right? So you usually sometimes you will write your C++ like this. It's because of one line can operate into several operations, and then we can store back to the result to the variables that will store the final result. So in this case, okay, assembly language can only operate one instruction or one operation. So in this case, for B plus C plus D plus D minus E, so means that you first can operate B plus C, and then the result you can add with D, and then the result you can sub with E. Okay, so the first one B plus C here, S1 plus S2. Okay, so ADD add, and then you will add the source $S1, comma $S2 as the B plus C. And then where do you want to store it? Okay, you can store on the temporary variables. Okay, any variable, temporary variables, register or $T0. And then once the result of T0 has been retrieved, so we can add to D. Okay, so you can add temp plus D. So T0, comma, register or $S3, and then the result can be stored back on the same temp. So $T0. Okay, so $T0, so can be added back again. And then last, okay, the result of them, okay, will subtract with S4, which represent E. Okay, which represent E. So T0 minus S4, the result will be stored in S0, which represent A. A is equal to temp, subtract E. Okay, so you might be wondering, madam, can I use a different method? Yes, yes. Here, another style is that A is equal to B plus C plus D minus E, right? So first is that I can add this first, B plus C. And then the next instruction, I can subtract. Okay, because the priority is the same. Okay, it doesn't change the priorities, right? Unless it is multiplication or division, that one would be different, right? So we would look at the priorities. So between addition and subtraction, they have the same priority. So we can divide into these two operations. So you can write ADD. Okay, so for B plus C, so we would store it on a temp1, okay, or $T0. And then for B here is $S1, comma $S2. Hashtag, okay, temp, or maybe I'll just write T0 is equal to B plus C. And then this one is subtraction, right? So you would sub. Okay, you cannot use T0 anymore. It's because it's storing the B plus C. Okay, so if you use T0 again, it would override the previous value. Okay, it would erase the previous value, which would become error on your calculation. So use another variable, temporary variable, T1 dollar, and then S3, dollar S4. So what happened if you miss the dollar sign here? It's like when you try to compile it, it will give you error. Okay, so remember, all registers must have dollar sign. Okay, so the C++ representation is T1 is equal to D subtract E. Okay, D subtract E. Now, we have both. Now, I would add these two results, okay, to get the final answer, to save into A. So, ADD, and then register A is S0, comma, dollar T0, comma, dollar T1. So, here in the comment is A is equal to T0 plus T1. Okay, so it can be in two ways. So you can answer these two ways. But compared to the performance, okay, compared to performance, the second version here can be used for parallelism. Means that if you want to execute these instructions in a faster way, you would divide the instruction, right? So this one can be divided and sort to another core processor. And then this one can be sort to another core processor, can be sent to another processor. And then we can combine the result, okay, by combining the result and then run the addition. But for this instruction here, they are waiting. Okay, you have to wait for this T0 to complete and then add another operation, do another operation while waiting for the taking the result of T0. Okay, and store back to the T0. And then the third expression or the third instruction here needs the result of T0, okay, to be written in the registers. And then we can subtract, okay, with another registers. Okay, so means that they have to wait for the previous instruction to complete. So which means they cannot be they cannot execute in parallel way. Okay, so notice that a single line of C may break up into a several lines of MIPS. So for you, when you try to write your C++ here, okay, you can write in a single statement. Okay, but for MIPS, you have to break up into several lines of MIPS. Okay, so if you have several operations here, plus, plus, minus, then you have to break into several MIPS instruction. Okay, so everything after the hash mark on each line is ignored because it was treated as a comment. So because we have a hashtag here, so they were treated as a comment. Right, and then how do we do this? Okay, so since we have a bracket, so you know which instruction that needs to be prioritized. So so we can use intermediate temporary registers. So to operate the first paragraph. Okay, so to the first bracket. Okay, the first bracket is G plus H. So this one would be execute first, and then this one would be the second, and then this one will become the third one. Okay, the third instruction. So the first instruction here is for G plus H. So S1, comma, S2, and then we would add. Use the command add, and then store it on $T0. Okay, T0 here is treated as a temp. And then I plus J. So I plus J is S3, comma, $S4, and then the operation is add, and then the result will be stored in a temp. Here we use T1. Okay, T1 is the temp. And then the last operation is to subtract the result of the previous instruction. So T0 minus T1, okay, the result will be stored in S0, which refer to F. Okay, so maybe you want to say that, oh, madam, if I use a different style, if let's say I would add and then I would subtract and then I would add back again. Okay, is it correct? Theoretically, if the value does not change, it will be correct. But in terms of the operation, okay, so maybe the G plus H would derive first, and then I plus J would be derived later on. So in terms of performance, it was not suggested. Okay, so refer to the priorities, right? And then this is I would explain about the usage of the registers. So one of the register was called 0. So one particular immediate called the number 0 appears very often in code. Remember when you try to declare integer I is equal to 0, right? Like this. Okay, so we can also define this command, okay, by using a specific register called register 0. Okay, so register 0 or $ZERO. So this is the name, this is the number to define the register 0. Okay, so when they create this register, so the functions of this register is that this register always have the value 0. For example, add ADD, okay, $S0, $S1, and then $0 here. So this is in MIPS. When you try to add, so basically it was S1 plus 0 equal to S2. Okay, so you just want to move, okay, or you want to not move, copy the value in S1 to S3. So thus came F is equal to G. So in fact, there's an implicit plus 0 there in the MIPS. Okay, so you can do it like this. Add S0, S1, register 0 to initialize the content of S2 with value of S1. Okay, so here we refer F is equal to S0. G is referred or associated with S1. Okay, so register 0 is defined in hardware. So an instruction of add $0, $0, $S0. So imagine if we write that, means that 0 is equal to 0 plus S0. Okay, so when you accumulate, okay, accumulate to a result of $0. So remember, $0, if you put any value on that register, it will always return value 0. Okay, it would always have the value 0. So means that you cannot write any value on this register. So it will not do anything. So in this case, we like put an idle instruction there. You put an idle instruction there. So this would be explained on chapter 9 uh, um, about parallelism. Okay, so this would be explained later on. Right, so immediates. We have immediates to represent numerical constants. Okay, so they appear often in code, so there are special instructions for them. For example, okay, we have ADDI, okay, add to represent add operation, I here to represent immediate. So means that the second source is a constant, okay. So first operand, the first operand must be a register. So here is S1, and then the second source is the constant. So constant here is written as 10. Okay, so it can be any positive or negative number. Okay, so here, okay, it can be negative or positive. Okay, so if we write ADDI S0, S1, 10, so in C, they are represented as, this one can be associated with G. So G, add means plus. So G plus 10. The constant 10 is stored into S0, which is associated with F. So F is equal to G plus 10. Okay, so we can also represent like this, X plus plus. Okay, so X plus plus, Allah. Okay, so X is equal to X plus 1. Okay, so it's equivalent, right? X plus plus is equivalent to X is equal to X plus 1. So you can write your MIPS as ADDI, okay, dollar. Okay, as X here is referred as S0, eh? So I would just refer this as S0. So dollar S0, comma 1. Like that. Okay, let's say X minus minus. Okay, so X is as 0. So I can write ADDI, okay, dollar as 0, comma, dollar as 0, comma, negative 1. Okay, so to represent X is equal to X minus 1. Okay, so minus here or plus here is put on the constant. Okay, you will put it on the constant. Right, okay, so syntax is similar to add instruction except that the last source is a number instead of a register. Okay, so as you can see, when I try to subtract X minus minus, I still use the command ADDI, right? Okay, so I still use the command ADDI. It's because of ADDI, the immediate can accept negative number. Okay, they can accept negative number. So we don't need the subtract immediate. So limit the types of operation that can be done to absolute minimum. So if an operation can be decomposed into a simpler operation, then there's no need to include it. So ADDI can subtract, okay, using a negative number. So sub I, okay, it can be said that, okay, like this, ADDI and then T0, okay, dollar T0, comma, dollar T0, comma, negative 1. It's also equivalent to sub I, okay, dollar T0, comma, dollar T0, comma 1. Okay, so it's equivalent. So there's no need to use the sub I. We can just use the add I only. So the reason is that the simpler it is, the much better for the CPU to operate it. Right? So here, so ADDI. Okay, so let me erase. Okay, now. Okay. So ADDI, so ADDI S0, S1 minus 10. Okay, so negative 10. So means here in C is F is equal to G subtract 10. So where MIPS register S0, S1 is or are associated with C variable of F and G. So here means G minus 10, and then this is F. We store it back on as 0. Okay. So and then the last the operation. Okay, so the operation in C variables map onto registers. So what if we are using arrays? Arrays. Okay, arrays in C means memory. You want to store it in a temporary memory, but you want to refer that back. So we use an array. So one of 5 components of a computer is memory, contains such data structures. Okay, we can store this array in the memory. But MIPS arithmetic instruction only operate on registers. So they never directly operate on memory. So remember, all the data is stored in memory. But when you want to operate it, you must transfer. Okay, you must transfer the data to from memory. So we have register and memory. So when you want to operate when you want to operate or when you want to do an instruction, data must be transferred to registers. And then when you want to store back the data to the array, so you want to transfer back to the memory. Okay, so one is from memory to register, we call it read because you want to read the data in the memory and store it to the register. And then if the data transfer from register to memory, we call it write because you want to store the result of the operation to memory. Okay. So here is like arrow. The arrow here shows the direction of the data transfer. Okay, so from memory to register, we call it read. And then from register to memory, we call it write. Okay, so let me look at the watch now. Okay, so it's 9 o'clock. All right. So right, so next is the anatomy. Okay, 5 components of any computers. So within the computers, we have processor, we have memory, and also devices, right? So within the devices, we have input and output. So registers are in the data path. Okay, so it's inside the processor. Within the processor, we have a control or what we call as the brain, and then the data path, which is the registers. Okay, so it's contained inside the registers, inside the data path. So if operands are in memory, we must transfer them to the processor to operate on them, and then transfer back to the memory when we are done. So means that we want to read. So if you want to read the data from the memory and write it to the registers, so you would say we load from memory to the registers. And then if we want to write, means that we want to store it back. So we call it as store from registers to memory. So these are data transfer instructions. Okay, so to transfer a word of data, we need to specify two things. Okay, so we have registers. Okay, you need to specify registers by using within all these registers. Okay, so register 0 until register 31, or maybe use a symbolic name, maybe S0 T0. And then another things is that we need memory address, which is more difficult. Okay, so think of memory as a single one-dimensional array. So we can address it by simply supplying a pointer to a memory address. So other times we want to be able to offset from this pointer. Okay, so the first time is that you need to point that memory. So this is a memory that we refer as a cell of array. So this is like an array. So you need to point out that array location. Okay, so this is pointer. It will point out the array location using the memory address. Okay, and then the next time we want to refer this memory, we can just use the offset. Okay, we can just use the offset. Maybe we need to jump. Okay, jump to the next cell. Okay, jump to the next address. Jump to the next address. So we just refer to this pointer and then jump to the next offset. So to jump to the next offset, so we need the pointer first, the memory address. So remember, the command is load from. Okay, load from memory. So to specify a memory address to copy from, okay, we need to specify two things. One is the register that will contain a pointer to the memory. It's like a constant. Okay, so when you try to point a register to become a pointer, so usually you will write it like this, int asterisk a. Okay, so like that you would tell a is a pointer. Okay, a is a pointer. Okay, so a pointer variable. So in this case, we also need to specify a register, okay, that will contain a memory address. Okay, it will contain a memory address. And then you also need a numerical offset. Okay, so offset here means how many bytes. Okay, how many bytes we need to jump from this memory address. Okay, so the desired memory address is the sum of these two values. Okay, so the desired memory address like this one. So let's say the memory address start at 0. So this one is in a byte. So remember, byte is in a 4 byte, 4 byte, 4 byte. So 4 plus 4 is 8. And then 8 plus 4 is 12. And then 12 plus 4 is 16. So remember, it is in a 4 byte. So 1 byte is equal to 8 bits. 4 byte means 32. Okay. So when we try to jump, let's say this is on, let's look at the question. Oh, okay, 8, right? So the value is on this location. Okay. So we would point the address to this first. Okay, first index of the array. The first index of the array is 0, right? So this is index 0, and then this is index 1, and then this is index 2, and then this is index 3, and then this is index 4. Okay, like in the array. And then the pointer. Okay, the pointer address would point to the first index of the memory. Okay, the first index of the memory address. So we will refer to this address 0, and then when we want to retrieve the data from index 2, so we would offset to x. Okay, so how do I derive that? 8. How do I derive that 8? It's based on the number of byte. Okay, the number of byte. So let's say this is index 0. Okay, this is index 0, index 1, and then index 2. Okay, so how many do we need to multiply to get it? So we just multiply by 4 because of one index contain 4 byte. Okay, one index contain 4 byte. So the size here is like a 32-bit memory. So only on this subject. Only on this subject. If you learn about operating system, they would define different type of size of memory. Okay. So this is only an example. So for MIPS, they use a 32-bit memories. Okay, 32-bit memories. So 32 bits in byte is 4 bytes. So since the size is 4 bytes, so each of these data, the first index contain 32 bits. The second array contain 32 bits. The third array or the third index, okay, contain 32 bits. So that's why we start at 0, 4, and then 8. So when you try to add, let's say T0 contains 0. So 0 plus 8, and then you will get the specific address that is pointed. Okay, that is desired. Sorry. That is desired in the coding. Okay. So here, if I say 8 here, and then with the bracket of T0, so it will specify that the memory address pointed to by the value in T0, okay, and then we will add with 8, then you will get the desired memory address. Okay. So what are the syntax? Okay, what are the syntax of memory to register? If we want to load instruction, okay, we want to load the data from memory to register, we still use the same syntax. 1, 2, comma, 3, but this time we don't have a comma, we have a bracket. Okay, you have a bracket here. So 1 here is the operation name, and then the register, 2 here is the register that will receive the value. So where do you want to store the value that you have retrieved from the memory? So in this case, we have 2 registers. So one is that the register that will receive the value. The second one is on the 4th column, which is the register that is containing the pointer to the memory. So in this case, okay, the register in column 4 here must not be touched to use other instructions. Okay, you cannot use for adding data and store it on these registers. Okay, so it's this register will become a constant register that is used to store the memory address. So this register is what we call as base register. Okay, so we call it as a base register. And then the third column here is for numerical offset in bytes. So how many bytes do we need to jump from the pointer memory here? Right. So now if you refer to the green sheet, okay, so to transfer from memory to register, we use the command LW, meaning load word. We load word from memory and then write to the register. Okay, so 32 bits or one word are loaded at a time. So example, okay, so we have load word T012 as 0. So remember, we read from the right side first. So here we have a bracket. So if you have a bracket, it will tell you this is a pointer. S0 become a pointer that contain the memory address of the data. Okay, because sometimes it doesn't have to point to index 0. Okay, sometimes it doesn't point to index 0. Right, so $S0, okay, is the base register. So this is a base register. Add with offset 12. So offset 12 here means that 12 divided by 4. So 12 divided by 4 is equivalent to 3, right? So means that if your array, okay, so your array is 3 here. Okay, so it's index 3. Okay, so the fourth cell in your array. Okay, so let's say if you were given an array instructions in C, so let's say array and then with the bracket 3 here. So what you need to do is that you need to multiply 3 here need to be multiplied by 4. So you will get your offset. Okay, so you will get your offset. So 4 here is referring to 4 bytes. Okay, but in this case, once you have the offset, okay, so index 3 times 4 bytes, so you will get the offset 12. So 12 plus the memory address in S0, then you will get the exact or specified memory address, and then we will retrieve. Okay, once you get the memory address, the CPU will retrieve the data. Okay, they will send the data back to the register and store it in T0. Okay, they would load it into T0. So I'll use the word load. They would load the value from the memory, okay, pointed by memory address in S0 plus 12. Okay, into the register T0. Okay, so offset is generally used in accessing elements of array or structure. Okay, so let's say you have student, okay, student 4. Okay, student 4, you want to retrieve or you want to load data in array student 4. So what would be your offset? So your offset would become, okay, offset would become, okay, 4 index multiplied by 4 bytes. So you will get 16. So then you can write load word T0 16. Okay, dollar S0 and then with the bracket. Okay, so that is how you want to write memory to register command. Okay, we also want to store from register into memory. Let's say you have done the operation and then you want to store back into the memory. So the store memory in or the store instruction syntax is identical to load word. So only that we use the command SW. SW means store word. So we will store the 32 bits or one word into the memory at one time. Okay, for example, store word T012 S0 means that this instruction will take the pointer in S0. Okay, this is the base register. We use back the same base pointer, right? So we are using the same base pointer. So in this case, we put it in a bracket. So to point the base pointer. And then add the offset. Add 12 bytes to it. So to get to the desired memory address. So 12 plus index 0 address and then store the value from register T0. Okay, so T0 value here will be stored into the memory specified in S0 plus 12. Okay, so remember, okay, the keyword store into memory so that you would remember how they are operate. So if it's SW means that you store from T0 to the memory. Okay, to the memory. All right. So it's a different data flow. Okay, different data flow. Right. A register can hold any 32-bit value. So that value can be a signed integer, an unsigned integer, and a pointer, and so on. So example, if you write at $T2, $T1, $T0, So means that you want to add an integer value contained in T1 and T0. So T0 and T1 better contain values that can be added. Okay, it must be a value that can be added. So another example is that if you write load word T2 offset 0 and then with a base pointer T0. So then this T0 must contain a pointer. Okay, must contain a pointer which in this case is memory address. Okay, it must contain memory address. So don't mix up. It's because of this register can contain any value. Okay. Right. And then every word in memory has an address similar to an index in an array. So early computers numbered these words like C numbers, like element of an array. So memory 0, memory 1, memory 2. Okay. So it will become like this, okay? Like this. Like I have draw it for you. So this is memory 0. This is memory 1. This is memory 2. Like that. But for the computer, they needed to access 4-bit bytes as well as words. So means that if we are using a 32 bits of 32 bits architecture, so then we have to use, okay, we will create or we design the memory, okay, so the memory that is read will become 32 bits. Okay, the size become 32 bits. Okay, so in this case 32 bits is one word. So today machine address, okay, today machines address memory as byte. Okay, so thus comes the word byte address. Okay, so they don't use the bits because the bits is too long. So they use the byte address to represent the machine or the computer address memory. Hence, the 32-bit or 4-byte word addresses differ by 4. Okay, differ by 4. So let's say for your index, let's say you use array 0, array 1, and then array 2, right? But in memory, this index are referred by, okay, memory 0, and then this is memory 4, this is memory 8, and then next. So here you can refer to 0 times multiple by 4, and then this one also 1 multiple by 4, you will get, okay, the memory address. Okay, so the memory byte address, we call it as a memory byte address. So byte address 4, and then for array 2 times 4 means memory 8 bytes. Okay, so address 8 byte address. So here means that the keyword is that you times 4. Next is that compilation with memory. So what offset in load word to select A index 5? Okay, A index 5 in C. So if we want to represent A index 5 in C, so here we take the 5 here and then multiple by 4 bytes, you will get 20 for the offset. So to select A5, okay, and then we compile by hand using registers. For example, G is equal to H plus A index 5. So G is represented by S1, H is represented by S2, and then S3 here to represent base address of A. Okay, to represent the name of the array. So the name of the array itself is a memory address. Okay, so memory address of the first index. So that's why we always call A here is A0 in C. Okay, it's also on C. the base address here is always referred to the first index of the array. Okay, so now first transfer. Okay, so let's say if you have this C++ expression, G is equal to H plus A index 5. So we need to transfer the data in memory to the register. So load word T0 as the temporary to get A5. Okay, and then the offset is 20 from the index here, 5 multiplied by 4 bytes. And then the pointer register, okay, is S3, right? Okay, so $S3 in a bracket. So now we have A5. We only have A5, okay? So next is that we add A5 in T0, okay, to H and place it in G. So ADD $S1, $S2, $T0. So here we can have T0 add with S2 and then store it in S1. So thus comes the expression of C S1 is equal to H plus A index 5. Okay. So notes about the memory. Forgetting that sequential word addresses in machines with byte addresses do not differ by 1. Okay. So in index or array, they are differ by 1. Okay. So array 1, array 2, array 3, array 4. But in assembly, okay, in assembly language, they differ by 4 bytes, 4 bytes, 4 bytes. Okay. So many assembly language programmers has toiled over errors made by assuming that the address of the next word can be found by incrementing the address in a register by 1 instead of by the word size in bytes. So also remember that both load word and store word, the sum of the base address and the offset must be a multiple of 4 so that it will be word aligned. Okay. So the memory organization is viewed as a large single dimension array with access by address. So a memory address is an index into the memory array. So it contains, let's say, the memory address is in 8 bits. Okay, 8 bits, 8 bits, 8 bits. Okay, and then 4 8 bits would contain would be grouped into one words. Okay, so a memory address is an index into the memory array. So byte addressing means that the index points to a byte of a memory and that the unit of memory accessed by a load or store is a byte. Okay, so they store it using a byte. So previously when you saw it, it is in an 8-bit, right? So 8-bit, 8-bit, 8 bits. Okay, so this is an 8 bits data. Okay, in a single dimension of array, but in a MIPS, okay, we operate using 32 bits or 4 bytes. So 4 bits, sorry, 4 8 bits, 4 8 bits data, okay, is grouped into one word. Okay, so one word. Okay, so but basically means that this is a 0, 1, 2, 3. And then when it goes to 4, 5, 6, 7, so it will become another, okay, another word. Okay, so the composition or the organization of the memory can be anything, but you just need to remember, okay, the organization in MIPS is that a word is 32 bits and then the data is stored in 4 bytes. So when they retrieve, when we load word or store word, they must be load or store in 4 bytes. Okay, like this data. So basically 0 here means that we have a composition of cell 0, 1, 2, 3. Here 4, 5, and then 6, and then 7. Okay, so it's like a cell of 8 bits. Okay, a cell of 8 bits. A cell of 4 bits. Sorry. A cell of 8 bits. So, and then we group it together to get a 32 bits of data. Okay. So thus come the 4 bytes of each of the memory. Okay, so when we arrange the byte, okay, into 4 bytes, okay, into 4 bytes, so the bytes can be numbered in two ways. One is that we arrange it from left to the right. Okay, so from left to the right. So here is from the left to the right. So byte 0 at the leftmost, most significant, become the most significant. To byte 3 at the rightmost, which is the least significant. So this is what we call as big endian. Okay, which is previously used in a power Mac. Okay, power Mac processor. Okay, so if I'm using like a MacBook here, but my processor is using a power Mac, then they would use this big endian. So the position of the byte start from the left to the right. So byte 0, byte 1, byte 2, byte 3. But another way is that they use a byte 3 as the leftmost bit. This one. Okay, so the leftmost bit. And then byte 0 is on the rightmost, which is the least significant. So this is what we call as little endian. Okay, little endian. Okay, so this is what we call as little endian. So little endian is used by our Intel processor. Okay, so you would read the byte from the right to the left. So start with the right, byte 0, byte 1, byte 2, byte 3, like that. Right. So in SPIM, memory storage depends on that of the underlying machine. So Intel 8086 are little endian because SPIM always show word from left to right. So a mental adjustment has to be made for little endian memory as in Intel PCs in our lab. So start at right first, then go to the left. Okay, so start at right of next word and then go left again. Okay, so that is little endian. From the right to the left. So what if more variables than registers? So let's say if you're using in your C++, we have more variables that we have declared. So compiler will try to keep most frequently used variable in the registers. Okay, so less common variables in memory would be repeatedly used. Okay, so less common memory in memory would be repeatedly used or would be replaced. So to avoid the spilling, so only spill to memory for less frequently used variables. Okay, so the less common variables that is not used, we can store it on the memory. So the register optimization is important. So the one that is most frequently used, then we would keep on using that variable as a constant, like a constant. So why not keep all variables in memory? Okay, so let's say if you want to keep all the data in the one that you have stored in the initialization, so you want to store in the memory. Okay, so you need to remember smaller is faster. So registers are faster than the memory. Okay, so register are the fastest. Okay, are the fastest compared to the memory. So in this case, memory here is referring to cache and subsequently the RAM. Okay, subsequently RAM. So basically they are referring to the RAM lah itself. But later on you will know actually the data are stored in the cache actually. Then registers are more versatile. Okay, so MIPS arithmetic instructions can read two registers and then operate on them and then write per instruction. And then MIPS also only read or write one operand per instruction and no operation. Okay, so that's why the registers is more versatile is because of we don't have to initialize or to specify or which registers are needed for the memory for data transfers and then which registers used for arithmetic instruction. So basically registers can be anything. Okay, so far all instructions only manipulate data. So we build a calculator sort of instruction, right? So in order to build a computer, we need ability to make decisions. So C and MIPS provide labels to support go to, jumps to places in code. Okay, previous version of C, they use go to. Okay, but in C, we use if, then else. Okay, we use if, then else. Okay, and then if we want to repeat, okay, if we want to jump to certain functions, we call the functions. Okay, we use functions to jump to certain instructions. Okay, so heads up, pull out some papers and pens, and then you can do an in-class exercise. So remember, if we have like if statement in C, usually the syntax will be like this: if condition, and then what are the clause that you want to write if the condition is true, so the clause here will be operated. Okay, also another if condition, if statement is that if, and then the condition, the clause one will refer to the true statement, else we execute the false statement. Okay, so clause 3 is referring to the false statement, right? So rearrange second if into the following. So here, if we write, okay, so if you write the, let's see. Okay, if x equal to 0, like that, so x is equal to 0, then we would run this statement. X is equal to x plus 1. Else, x is equal to x minus 1. Like that. Okay, so we know that, the condition. Okay, so if we run the if condition, go to L1. Okay, so to write this, statement, okay, so we want them to execute this L1 here. Okay, so this one is L1, and then this one is condition for L2, clause 2, clause 2. Okay, so this is a condition. So if we write if, if condition, is true, so jump L1. Jump L1 or go to, we go to L1. So go to L1. Okay, no need go to, we just write jump. Okay, we just write jump. So jump L1. Okay, and then okay, so sorry, this one is L1, and then this is clause 2. Okay, so this is clause 1, and then this is clause 2. Okay, hold on, someone is calling me. Right, let me continue. Okay, so if x is equal to 0, and then we will run, if the condition is true, we will run this clause 1, else we will run clause 2. So let's say if we use the same condition here, we would jump L1. Okay, so next instruction that we execute would be clause 2. So it says here, if the condition is true, we need to jump to L1. L1 here contain clause 2. Clause 1. So here it says that, okay, if the condition is true, we would run true statement here. through statement. Okay, we will run through statement here. So they will jump to L1 to execute through statement, which is the clause 1. Else, okay, else they will go to the next statement, which is the clause 2. So there's no else instruction in the MIPS. Okay, in the MIPS. So you would place the structure of the MIPS like this. So let's say if the condition is true, we would jump to somewhere to execute the true statement. Else, you would write the false statement here. So you would write the false statement here. Okay. So, alamak. Go back. Okay. So not as elegant as if else, but they have the same meaning. Okay. And then let's say you have run the clause 2, right? You don't want them to run the true statement here. If you look at on the C++, okay, so once we have run the x is equal to, or the true statement here, x is equal to x plus 1, then they would not run the else statement. They would jump to the next main bodies, right? So it's also the same condition on assembly. So once you have run the clause 2, we jump to L2. Okay, so jump to L2. So L2 here means something else, or the main body of the codes. Okay, the main body of the programs. So we can run anything. So anything, So meaning that continue with the body with the main function. Main instruction. Okay. So that is for the if statement. So let's say, okay, you want to compare. Okay, you want to compare or to write the condition. So condition is usually if x is equal to 5, or x is less or equal to 5, right? So usually we use the command compare. So when we use the command compare, the command for compare is B. Okay, command for B means branch. Okay, branch. Okay, and then EQ means equal. Okay, so branch equal, branch not equal. So you can see the commands used in branch. We have two only. Branch equal, branch not equal. But let's say if you want to use, let's say if x is more than 0, more than 5 lah. Okay, so if x more than 5, okay, so more than, so we cannot, we cannot use the branch, but we can use set less than. Okay, we can use the command set less than. So it's equivalent to less, like this. So set less than, you convert it. Okay, you need to convert it. So set less than is set less than x, okay, sorry, t0, t1. Okay, this is T0, not 2. Okay, dollar and then dollar. So this means, okay, if you write SLT T0, T1, so this means T0 is less than T1. So T0 is less than T1. So if you want to convert X is more than 5, so you can convert 5 is less than X. Okay, so you can represent 5 into T0 and then X into T1. Okay, so you need to play around with the command. So you only have the set less than, or you can have set less than immediate. So you have set less than immediate, set less than immediate unsigned. So this can be used. Okay, so okay, go to the slide. So we are using a branch, means that we need to compare only. So if register is equal to register 2, we will go to L1. Or if it's not equal, so we can use branch not equal. Okay, you can use branch not equal, register 1, register 2, and then L1 here is referring to where you want to jump to. Okay, where you want to go to. So L1 here is referring to the label. It's not a variable, it's a label. Okay, this is referring as label. Okay, so if you write BNE register 1, register 2, L1 means that if register 1 is not equal to register 2, go to label 1, L1. So this is what we call as conditional branches. Okay, so and then in addition to conditional branches, we also have unconditional branch. So we can also use the command J or jump. Okay, jump to a label. Okay, so we call a jump operation jump directly to the given label without needing to satisfy any condition. Means that you don't need to test any condition. So you just simply jump it. Okay, so it's the same meaning as go to label. So technically, it's the same effect as BEQ. Means that is register 0 equal to register 0. We jump to label. So since it always satisfies the condition, right? So 0 is equal to 0. Yes. So we just jump. Okay. So now we can try to compile C if into MIPS. So let's say we use this mapping. So if I is equal to J, we would execute the true statement F is equal to G plus H. Okay, else, okay, if it's false statement, then we would execute F is equal to G minus H. Okay, and then make sure to exit. Okay, so use this mapping of S0, S1, S2, S3, and S4 to represent F, G, H, I, J. So, let's use the command here. Let me make it smaller. Right, like this. Okay, so I hope you can see it. So let me write back again. So if I is equal to J, okay, then we want to represent F is equal to G plus H. Else F is equal to G minus H. Okay, so now okay, you don't need to write the clause. Okay, you don't need to write the clause. We just represent it. Okay, you just need to represent F is equal to S0, and then G is equal to S1, H is equal to S2, and then S3 and S4, right? So IJ is referring to S3 and S4. So we can just use branch equal and then use for I and J, right? So $S3, $S4. So this is for branch. And then where do we need to jump? Okay, where do we need to jump? So using this condition, we convert back again. So we convert back branch equal here. Okay. So if I write it like this. This become a command. If condition S3 is equal to S4, we would jump to L1. So L1 here is for the F is equal to G plus H, right? So G plus H is ADD and then dollar, what is F? What is F? S0. Okay, dollar S0. Okay, and then dollar S1, comma, dollar S2. Like that. Okay, so copy this to represent the clause 1 in label 1, like this. So true statement is F is equal to G plus H. Okay, and then for clause 2 is sub register S0, register S1, register S1, register S2, like that. So it's also the same. Okay, so we put it on the clause 2, like this. So my false statement is F is equal to G minus H. Okay, and then once if let's say the condition is false, so they would run the sub here, and then don't forget to put jump L2, right? So don't write jump L2, you just write J. Okay, so J here means jump L2. Okay, so that is how you want to write your coding. So jump here. Okay, so on the next slide, they show you how to write in the MIPS. Okay, they are using true for true statement. Okay, so true for true label, and then fin here is to exit from the if statement. So I can also use like this. Here, write it true. Okay, it's a case sensitive. Okay, this is a case sensitive. So you need to remember this to write it exactly as what you have written on your code. So here is true, then and then I want to exit. Okay, so I'll just write exit. So here I'll write exit. Okay, but usually I would use like label 1, label 2. It's because of sometimes you have more than one if. So if you have more than one if, you cannot use the exit. So maybe you would use label like this. Macam ni. Label 1, label 2, label 3, label 4, like that. Okay. So you can convert into this using this style. Okay. So that's it. This is an exercise that once you have learned about the pointer, then I would ask you these questions. Okay, so now we are done. Okay, so we have left only 2 minutes. Okay, so I'll see you next week. Okay, so I'll see you next week. So do you have any questions? So those who want to